motivation for creating our robot was to develop our skills as professional engineers, not just individually, but as a team. Our aim was not to just meet the criteria, but to challenge ourselves and display individual talent.
The design of the robot was heavily influenced by the need to accommodate our chosen drive system. Stepper motors were selected very early in the project due to their low cost, high torque, and simple yet reliable open loop operation. The orthogonal wheels are isotropic and have the advantage of constant radius ground contact by having at least one wheel in contact with the ground at any time. This provides a smooth platform for the vision system. Like other Omni wheels, they have a driven direction and an orthogonal passive rolling direction. With 3 motors and the combination of passive and driven directions of the wheels, the robot is capable of rotating and moving in any direction, controlled by the sum of the velocity vectors of the motors. In early testing, a simple rubber band was used to stop the ball from rolling away from the robot. However, this was later replaced with a motorized dribbler to provide the ability to pull the ball from walls and obstacles. The dribbler spins the ball into the robot, allowing the robot to reverse and rotate while maintaining control over the ball. A solenoid kicker was squeezed between the motors and under the dribbler bar to give the robot the ability to kick the ball. Custom making the solenoid allowed us to design it for operation at 12 volts while maintaining high power by utilizing the high current capabilities of lithium polymer batteries. This allowed us to eliminate the need for complex boost circuits and costly capacitors.
I was in charge of the electronics and software on the soccer robot. The electrical system was responsible for providing an interface between the high-level modules such as nav and vision to the mechanical system. These interfaces included motor control, kicker interface, and dribbler interface. The specifications for the electrical system included 3 stepper motors with velocity control, an 11 amp 12.6 volt kicker power circuit, and a 12.6 volt high-speed dribbler motor. A USB module was provided for the navigation. The navigation could then send magnitude, angle, and angular velocities to the drive system, which then would be converted into separate motor velocities. The stepper motor velocities were controlled with an acceleration profile. This acceleration profile was all calculated on the embedded system, therefore requiring no more calculations to be done on the phone. The kicker circuit was based on a 40 amp automotive relay. This relay was switched with a transistor from the microcontroller. The kicker was powered off a separate lithium polymer battery, allowing for high power to be isolated from the drive board.
Hi, I programmed the navigation of the small size Leap robot. In RoboCut, a robot's movement vector should never cut through another robot. Also, the robot should never collide with the walls. On top of this foundation, the robot should be able to acquire the ball deliberately and dribble it to the correct goal. Behind the robot is a model-based reflex agent. This means that the robot's movements are purely reactive based on what information it perceives from the environment. With different environment conditions, the robot will go into different states. For example, if the ball is not seen, the robot will go into a search state. Once the ball is found, it will then go into a chase state. At all states, the robot will avoid collisions. The foundation of obstacle avoidance is based off potential fields navigation method. In this method, there are attractors pulling the robot and opposers repelling the robot. Generally, the ball is attracting the robot to move towards it. However, the movements of the robot will be altered by the obstacle's repulsive force. But one of the disadvantages of this navigation method is the local minima, where the robot is attracted by the ball but repelled by the obstacle with similar force. This causes the robot to hover around and get stuck. When this happens, it should realize that it is stuck in the local minima and take other actions instead.
I was responsible for the vision for our small size league soccer robot. The vision is a subsystem of the robot which sits atop the entire communication protocol. It was the robot's only connection between the physical world and its digital interpretation. The vision system ran within an Android app running on a Samsung Galaxy S3. All processing was carried out onboard the phone. The necessary information was piped through to the navigation system so the robot could act appropriately. The Android app running the majority of our high-level control utilized an open source image processing development kit called OpenCV to launch the camera and capture each image frame. After this, custom software was written to allow us ultimate control over the remainder of the image processing. This led to higher frame rates and easier debugging. The final product was capable of distinguishing between all different types of field objects, such as the ball, walls, the goals, and other players. This image information is then converted into a vector, then relayed to the navigation system.